Hello everybody, this is again the MATLAB and Simulink Racing Lounge. And as you can see again in today's session we have a team featuring us and helping us to explain a certain topic. Glad to have the guys from Global Formula Racing GFR on board. We are going to talk about torque vectoring. Torque vectoring in general, we will talk about controller design, controller tuning, and one thing that I'm really curious to hear about is testing and tuning of that. So glad to have you on board, Florian and Vincent. Hello.
Hello, Christoph. My name is Florian, and I'm a member of the GFR, and I'm responsible this year for the control system design.
Okay.
Hello, my name is Vincent. I'm responsible for the vehicle dynamics controller and the overall e-powertrain system.
Okay, perfect. So seems that I have the right guys on board. And what are we going to talk about today? So we will talk about the motivation for vehicle dynamic control modeling. So of course, with a special focus on torque vectoring. We will talk about your approach for parameter identification, so for controller tuning. And last but not least, and I'm really looking forward to that, we will talk about testing and application, so validation of the test results. So thanks again for joining that episode. I'm handing it over to you. So the stage is yours, Vincent.
So what's our motivation? So as every Formula student team, we want to be the fastest, or we want to have the fastest car on track. And for this, we want to use the vehicle dynamic control systems to have better lap times on the track. Another stuff is all teams knows we have limited test days, so we want to do as much as possible with simulation. So we have more time with testing the driver, and get a reliable car. For this, we use simulation to reduce the real testing time.
Okay. Well, especially the second point makes perfect sense to me. Of course, the first one as well, because every racing team wants to be fast. But I'm really curious about your approach, how you reduce testing time by, well, using simulation in an efficient manner. So makes perfect sense to me.
Okay, now I want to start with the torque vectoring controller development, which is one vehicle dynamic control system which should make our car faster on the track.
Okay.
As every controller structure, you have to define a design criteria for your controller or a goal for your controller, because without a goal, you cannot achieve something. Yes, and for us, this is a still linear behavior of the car during high loads. So this means that if you're driving you're very high or very fast the curve, you also want to have a linear behavior of the car. This is pretty useful because drivers in Formula Student are just hobby drivers and not professional racing drivers like in Formula One. And a human can pretty good handle linear systems. So if you have a linear system or a linear car, then the driver is automatically better.
Okay, that perfectly makes sense. And I would say even a professional driver, for example, in Formula One, would be happier with a controller behaving linearly instead of chaotically. But still, he would perhaps be better able to react on that. But in that, I think the main criteria for you is easy handling, right?
Exactly, that's the point.
Okay.
So, and yeah, how can you achieve, or what you have to keep in mind is like the PID controller is not the fastest controller, but has a pretty good high accuracy. So you need on one hand the PID controller, but on the other hand you need a fast feed forward, which is much faster than the PID controller, but is not that accurate as PID
not as
controller.
accurate.
So combining two structures together, you have an optimal controller structure.
Okay.
And it's in case of torque vectoring, you have to take care about some constraints. In torque vectoring development, this is like the maximum transferable friction force, which is limited by the circle of forces, or as it's called in German, Kammscher-Kreis. This means basically you have a limited maximum transferable force. So if you are transferring very much force into X direction, you cannot transfer much force into Y direction.
Okay, perfect. Thank you. Just a question at that point. So as torque vectoring is a controller which controls the lateral dynamics of the car, do you also have a system controlling the longitudinal dynamics of your car?
Yes, that's right. We also have traction control, which controls the slip of the car of the wheel. So, and this traction control mainly controls the longitudinal force of the car. And as we said, due to the circular forces, the maximum transferable friction force is limited, and then you have to define a trade-off between the controllers.
Okay, so what would be interesting to see a sketch of your controller structure so that we can see how you all put that together in a model.
Yeah, we prepared the next slide for this to show our main controller structure for TalkBack.
Okay.
So basically it's just a normal controller structure, not very special. It's like, as you can see in the green box, this is our desired value generator, which calculates out of the current vehicle movement desired vehicle movement, or it's calculating out of the driver inputs and the current vehicle movement.
Okay.
And
what I see here, it's based on a single track or a one-track model. Why did you choose that kind of modeling?
Because we want to have this linear behavior, and as everybody know, we have there the one-track model is the linear model, and also the linear model, the one-track model is has just a few parameters, not like a two-track model, and this is basically for parameterization. It's very useful to have not much parameters, because it's not very useful to have like hundreds of parameters you can define. That's too much, and then you will lose time during testing.
Yeah. Okay. Well, it seems that it's easy enough to achieve the goals you have.
Yeah. So this desired value generator and the current vehicle movement are inputs for a PID controller and a feed forward, which are shown in the orange boxes. And these two boxes calculating additional yaw moment. So basically we are calculating additional yaw moment, which is put on the wheels. And this putting on the wheels is done in the red box, which is called wheel assignment.
Okay.
And as we talked in the last slide about the error correction, or the correction factors which define the trade-off of the controllers.
Okay, trade-off between longitudinal and lateral controllers.
Exactly. So this is done in the white box. So we here have the values from the other controllers, which are defining now a trade-off between the lateral and the longitudinal controller.
Okay, perfect. So from my point of view, that it's a very clear design, perfectly makes sense. Thanks for sharing that.
So, thank you. And now we want to have a little software demonstration about parameterization and how we use our torque vectoring, what we're doing. And now I want to hand over to Florian for this.
Okay, perfect.
First, I want to introduce you how we implemented our optimization with car model. For the car model, we used the car maker model by IPG, and we implemented our vehicle dynamic control structure into the Simulink model. Like you can see here, we do a closed loop simulation with the vehicle dynamic control system inside, and closing this loop with the vehicle model and the driver inputs for sure. Okay, now I want to go over to show you how we implemented the parameter optimization step by step, and what are the steps that should be done to get the optimized parameters.
Okay, perfect.
First, you have a rough estimation of the controller parameters based on the physical behavior of the car, like how much yaw moment you will need to achieve a specific yaw rate, and for that you will set the first rough parameters. Next step is to optimize these parameters, because the very rough parameters will not work very well in the real car. For this, we designed an object function with specific requirements of the controller, like a low response time, defined overshot, no oscillations, and high accuracy.
Okay.
This object function is handed over to the parameter optimization. Finally, we will receive the optimized controller parameters like P, I, and D part and also the actuation limits of the controller.
Okay, perfect. Let me ask the question at that point. So what kind of software tools do you use for the parameter optimization?
We don't use the design optimization by MATLAB Simulink. We wrote our own MATLAB script, like I mentioned, the object function, and we use the MATLAB function fmincon to optimize these functions.
Okay, perfect. And for our viewers, this is exactly the spot where you are already saving time, because you're tuning your controller in a simulation environment, and you don't have to rely on a lot of test data. So I think at that point you have definitely chosen a very good and the right approach at that point.
Yeah, fine. But finally, you have to validate these parameters for sure on the track, because if the controller, because one point is that the car model is not fitting to 100%, and the other point is what is much more important, that the driver feels comfortable with the controller setup.
Yeah. Well, I think that's something we know. It's not possible to develop a fast and reliable race car without testing. So we always have to rely on proper testing of the actual race car.
Yeah, for sure. Like I mentioned before, I want to show you now the MATLAB script which we use to optimize our parameters. First part of the MATLAB script is where we define our boundaries of the parameters which we want to optimize.
Yep.
The next part is the start values of the optimization. And finally, we wrote an object function which we hand over to the fmincon function by MATLAB to optimize, say, these function. Finally, you will receive a result which I will show you now.
Okay, perfect. So can you just comment a bit on the CPU time? So I assume that this optimization, well, as it is running several times, so what simulation time did you see with your computer?
At this computer which I use, you will need maybe one night, a little bit shorter than one night.
Okay. So, but it's a common laptop, so you're not running it on a cluster, just
no, it's a
normal
common laptop, yeah.
Okay, perfect. But well, at the end, you just have to do it once, or well, you don't have to do it anytime. If you find an optimal set of parameters, basically you're done.
Yeah, for sure. And you can go on the test track and finally do the fine tuning of the parameters to fit the needs of the drivers.
Okay, makes sense to me. Perfect.
Okay, now let's switch over to a cutout of the results from last night. Here you can see the first plot. On the y-axis the torque, and on the x-axis the time. The orange and the light blue line are the torques which are directly applied to the wheels, and the red and the blue line are the torque vectoring torques.
Okay.
These torques are a little bit lower than the torques which are applied to the tires. That is caused because the other controllers also interact with the full control system.
Okay, so let me ask the question at that point. So right before 24, timestamp 24, we see a step function. So where does it come from? Is it a driver input or is it a controller response? So what do we see here?
Yeah, for sure. That is the driver input. The driver is performing step steer. This part of the optimization is used to optimize the response time of the controller.
Okay, got it. And then, well, we see that the signals are keeping a certain level for, well, a small time, a little less than a second, or a lot less than a second, and then it's decreasing again in steps. So where actually do these steps come from?
These steps are coming from the sample time of the controller, and it finally it finally decreases because the step steer is only very high at the beginning of the step steer, and finally you achieve the vehicle behavior.
The desired value. Yeah. Okay. Cool.
The other figure I want to show you is the response of the car and the desired car behavior, the yaw rate.
Okay.
The yaw rate is on the y-axis and the time is also again on the x-axis. You can see the desired yaw rate is a brown line and the actual yaw rate is the red line. And you can also see the feedback of the car is very good. We achieve a low response time and
yeah, exactly.
No overshoot.
Exactly, no overshoot. Well, seems to be a pretty robust and smooth controller at that point.
Yeah, for sure. Now I want to switch back to our presentation and I want to show you finally something about testing and application of these control systems.
Okay.
So now let's switch over to testing and application of these control systems. Before each test day, we define certain goals for this day. We specify which sensor data we will need for finally post-processing of it. And we also assign the time for each goal which we want to achieve. And for sure, we specify tracks and maneuvers. For example, for torque vectoring, we define certain tracks, and we also define for the traction control certain tracks, like the acceleration event.
Okay, just out of curiosity, for example, for the acceleration, do you actually use the torque vectoring there? Or do you switch it off as there is no cornering and you just need the longitudinal dynamics controller?
Yeah, like you mentioned, there's no use of the torque vectoring controller. We have an individual traction control, so we don't need the torque vectoring controller here. Another point that is very important for us is the driver feedback, which I also mentioned before. If you design a controller and the controller reacts not very like the driver expects, it's very hard for the driver to achieve very good lap times. And also, as Vincent said, a linear behavior of the car is the goal which we want to achieve. The feedback of the driver, how he feels in the car with the controller setup, is a very important.
Yeah.
Finally, after each test day, the test day is not very over. There are two certain points or tasks which have to be done. The first part is to validate our car model with the testing data which we gained over the day, and also the control system analysis to look over the testing data and see where are the potential to achieve better lap times, to achieve a better controller behavior. Yeah.
Okay. Basically, what you are saying there is a very important point. So actually, you putting your test set or your test data and your model data together, and then how is your strategy in order to optimize the control system? So starting with the data you have acquired, what are your decision criteria? What are you doing then?
We look on the lap times which we achieved and compare it with the controller setups of different controller setups, and also with the driver feedback of each each setup, and then we can decide, okay, there we can take a closer look and maybe simulate it again with the car model and do a little fine tuning.
Okay, got that.
The other part is to validate the car model. For that, we use the input variables like steering angle, brake pressure, the torque commands on the rear axle for the car model, and we perform an open loop validation. And out of these simulation, we get the variables like wheel speed, yaw rate, etc. And we finally evaluate it with a MATLAB script. Okay, you can see here two plots. The first plot are the wheel speeds of the car, and the second plots are the acceleration of the car in longitudinal and lateral direction. The dotted lines are the input of the testing data, and the solid line are the output of the car maker open loop simulation.
Okay.
Like you can see here at the second 10 of the wheel speeds, you can see some spikes. These are caused because the real car is maybe at the very limits of the car, and because the car model don't fit to 100%, it might be caused that the car model will slip away.
Okay. Well, you've started to explain a bit about the let's say the worst part of that graph. But let me say, all in all, the correlation between model data and actual test data is pretty good. So apart from that behavior around time second 10, well, we have a pretty nice correlation actually between tested and model data.
Yeah, thank you. Now let's switch over to the acceleration plot on below. You can see the red line is the lateral acceleration and the blue line is the longitudinal acceleration. And if we think back what Vincent says about of the circular forces, we can see here a very good example. For that point, we can see a very high lateral acceleration at very low longitudinal acceleration.
Okay. Got that. Well, perfect, makes sense. Either you have very high longitudinal or very high lateral. Could I see what kind of track that is? So based just on the accelerations?
Yeah, sure. If you take a look on the accelerations at the beginning of the track, you can see that the car is performing a slalom because of the switching of the lateral accelerations from minus to plus and minus to plus.
Okay. Yeah. And again, the correlation between modeled results and actually tested results is pretty good for the accelerations.
Yeah, thank you. Finally, a last plot. It is about the roll, pitch, and yaw rate. The fitting of these plots is a little worse than the other plots. That is caused because the roll and pitch rate is very noisy, because our race car won't roll and pitch as like it yaws. That is caused because of the suspension setup. If our car will yaw like if our car will roll or pitch like it yaws, it will crash into the ground for sure.
Yeah, okay. Well, it makes perfect sense because the yaw rate is the actual cornering. That's something desired. And rolling and pitching is not so much desired. That's why you have your suspension system in order to absorb these loads. So for me, it makes perfect sense that the yaw rate is pretty high at that point. So some comments on that. Are you happy with the correlation of tested and modeled yaw rate at that point?
At some points, if the car is at the limits, the correlation is a little bit bad. There is potential to optimize the car model for sure. There's always the potential to optimize the car model because you want to achieve nearly 100% with the car model.
Yeah. Okay. But I think there's a very, very popular saying, so all models are wrong, but some of them are helpful. And I think in that case, your models are definitely helpful, although they are not 100% right.
Okay, yeah, thank you.
So, and I guess that already brings us to the key takeaways of today's session. So basically, we have seen a very nice approach of torque vectoring. You're stating that it allows faster lap times and improved reliability. So can you comment a bit on that?
We cannot present any data in case of time, but we gather from our driver feedback that they feel more comfortable with the torque vectoring in the car. And
okay.
Yeah.
Okay, perfect. So it's easier to drive. The drivers are happy with that. I think that's a very important goal that you have achieved here. When it comes to the para-optimization, so let me comment a bit on that. So it perfectly makes sense to me. You set up a controller structure on a basic level, and then you do the tuning using a simulation model based on a car model. So at the end, I think it definitely makes sense what you write at the third point, make the best out of a test day, it also perfectly makes sense. Can you comment a bit on, well, what would actually happen if you don't do that parameter optimization using simulation? So, and this leads to the question, so how much time did you save by using that approach?
I think I cannot tell you a certain time which you will save if you use parameter optimization, but I can tell you my estimation which time you will save. If you want to tune all these parameters only on track, you will need, I think, more than 1 week only with testing and application, and that is a huge number if you have less testing time.
Okay, well, and this is for sure, test time for any Formula Student team is somehow limited. And so this approach that you've presented to me perfectly makes sense. I'm really impressed. Well, this brings us already to the end of today's session. So what I want to do, I want to thank you, Vincent and Florian. So thank you for sharing your work. Thank you for sharing your opinion on that. Really was nice to have you in the session. Thank you very much.
Thank you.
Yeah, thank you, Christoph, for your opportunity to show our control system design and optimization of the parameters.
No, you're very welcome. And this is a message to all the teams. If you have something interesting to share, let us know. And before I forget it, congratulations again. With that approach, you also have won the Simulink Student Challenge. So congratulations for that. It seems that it's pretty robust and solid work. Okay, and this brings us definitely to the end of today's episode. So if you want to watch further movies of the MATLAB and Simulink Racing Lounge, just follow the link mathworks.com/racing lounge. If you are interested about all our offers for Formula Student teams, just go to mathworks.com and FSG or to the Formula Student webpage of your competition. And as usual, we are very interested in receiving your feedback. Not just feedback, but also ideas or comments. Let us know via our team email address, which is formulastudent@mathworks.com. And on our Formula Student webpage, you will also find a link to our complimentary software offer. So you will receive a big bundle of tools just on that. It's free for you. You may use it as a Formula Student team. And if you do use our support, if you do use our software, we would appreciate if you put our logo on your car and on your reports for the judges. Thanks again for joining that episode and see you next time. Bye bye.